Mic's working. Desktop audio's working. Okay. Okay. Now I just need to get back to here. Where'd the remote go? Okay, there's the remote. And now I just start Rec Room and we do the whole process again. Okay. Rec Room. And I need to join camera. Okay. Um, okay. Oh, I need to start recording. Okay, start recording. There we go. Okay. And go to. Okay. Okay. Not bad. Okay, so headset's recharged. Headset's recharged. So yeah. Oh wait, I gotta set up for the slide. Okay, like that. Okay. Grab the remote. Okay. So okay. So um battery's back. So back into everything. Um we're doing training. We're going to cover the basics, blah, blah, blah. We're going to go a little more into the advanced architectures. Anyways, so oh, oh, I'm just going to retry that. Okay, headset is charged again, so we're just going to continue where I left off. So yeah, training, we're going to cover a bunch of different types. And yeah, so I should make it so the camera is there. Okay, so pre-training. I guess if I'm doing that, okay, I guess I'll try again. Okay, yeah, headset's charged. We're gonna get back into our training section. So we just finished the entire architecture behind me. Okay, so well, my joystick's acting up. Okay, I got it this time. Headset is charged. So we're back. We're back. Headset's charged. I'm going to get back into training. So we're going to cover the basics of it. So pre-training and then keep going from there. So, okay, first, pre-training, where literally everything begins. Um, that model, the large language model, GPT-3, has literally nothing without pre-training. It's all a bunch of random values for all of those red matrices, all of the learned parameters, everything's randomized. So pre-training is where we can start making those not randomized. So, um, yeah, GPT-3 isn't that smart. Why is that? Well, pre-training is an interesting type of training because it's the base foundation. So it's just, how do I put this? We're just throwing words at it. All that it's given is a sentence, transform that into whatever numbers, and it just has to learn what it can. Half a terabyte, half a whole terabyte of stuff is just thrown at GPT-3, and then it has to learn. It's kind of hard to learn if you don't know English, if everything's just a bunch of numbers, a bunch of vectors. So you don't really expect GPT-3 to be the best with just pre-training. So thanks to all of that math, all of the complex things that happen, we're able to get something where you can ask it things. It's not going to be anywhere near like GPT 3.5, which came out in November of 2022. That can like respond and give answers to questions. This thing with just pre-training is just going to give you the next word. It's not going to answer any questions. It's not going to give you details or any format. So that's what pre-training is, just a foundation so we can understand the concepts of language. So mathematically, the reason I'm not getting into this is because that math is really a pain. If like it's not intuitive. It is kind of, but you need to know have a really solid math foundation. And there's a lot of rotating matrices and doing backpropagation and calculus and derivatives. I don't want to get into that because I personally, I I've already done my share of trying to interpret all of this, and I'm done with it. So maybe I'll make a video on it later in some other day, but no, not today. So how does pre-training work on a intuitive level with a little bit of math? Well, if I have the sentence, wow, I can't believe that worked, and we want it to generate this sentence. So we'll start with the word wow, and we just want to say, hey, GPT-3, I know you don't know anything, but here is what I want. Here's what you should be saying. So when given wow, you should generate, I can't believe this worked. So we run it through, and as you can see, the outputs aren't horrible. The word I is in there, so it is kind of understanding, or we do kind of have something to work off with, but it's not as high as we want it to be. It's at like what is that, like 23%? 37%, yeah, 23%, which is lower than the other two, meaning it's not likely to get picked. So we do something called, we're basically, we're going to tweak these values. We're going to say, hey, so we want the value for I to be much higher than all the other ones. So we'll set it to like 35 and lower the odds for you and that to 23 and 30%. So the way we do that is we give it that final goal of the 35% I, and then we tweak the values going backwards. So how do I tweak the reverse word embedding table? How do I tweak the feed forward network? How do I tweak the values of the multi-head self-attention? And then lastly, how do I tweak the input embeddings in the very beginning? And this isn't just like one at a time. It's how do the changes in the word embedding at the very beginning, at the very beginning, how does that affect the multi-head self-attention? And how do we change the multi-head self-attention to accommodate those changes, the next changes, and the next changes, so on? So it's a chain. That's why it's backpropagation. Everything depends on its previous values. So what that looks like, what you can think of instead of calculus, is it starts with like wow, that. Not really what we want. So what we can do is like maybe subtract zero point 0.6 from some parameters in the query matrix. Position, sorry, in the position encoding matrix. I cannot read the slides like this. But yeah, anyways, um, the position matrix, we'll just tweak some of the values there. Okay, now we're getting wow who. I don't know, is that better? We'll just try changing something else. Wow, okay, it's doing a little better there. So now maybe we can change something in like the query matrix, or in the next step, we can change something in the embedding. And by the end of it, we've turned those dials, those knobs that I mentioned before with parameters, so that now it's generating what we want. So it's just this kind of, here's the answer that you should get, even if you're not getting the right answer. Okay, well, I'm not looking at the camera. There we go. So even if you're not getting the right answer, we're going to tweak your values until you get there. That's all pre-training is. Nothing special. It's just math, math, math. So the results, it's not bad. So pre-training, given something like this, so the capital of France is Paris, where we want it to predict the word Paris. So we'll give it the capital of France is, and then it finishes that sentence. Or we have there's 16 ounces in a pound, red and yellow, green, orange, whatever, just autocomplete. And what this learns using this strategy is basic sentence structure, so grammar, um, factual correlation, so Paris, France, that kind of stuff, basic associations between words, so that's just like how things relate to one another. And then distributional means like how often does the or and or a bunch of words like that, how often do those appear across the entire data set that is given. And then that is shown based on how it generates. So if you give uh, if you give the model a data set, and a data set is like the wow, I can't believe that worked. It's just like a million of those sentences. It could just be a book. It could just be a straight up book. But what happens is, if that book has 10,000 letter 10,000 instances of like the, or like some very unique word, like I don't know, like cardboard, and it says cardboard like extensively way more than all the other words, you'll definitely be able to see that in how the model generates. You can think of it as, this pre-training phase as like a little baby GPT, like understanding like, oh, I can talk. This is blah blah blah, just a little blabber. Of course, it's much smarter than a baby, but it also isn't, and I'll explain that later. But yeah, so basic grammar, little baby mode. But the next step after pre-training, instruction fine-tuning, that is training, servitude. We're going the next stage, the next level. Now, instead of just letting it learn and grow, we want it to help us, damn it. So instead of having these nice autocomplete little facts for fun, now we have this. And what we're providing isn't just like instruction and then expecting response. We're giving it instruction and response, and that's what it's learning off of. So now it learns how we want our answers formatted, how we want our answers to a homework question or an essay summary or basic question, how we get all of those formats is through instruction fine tuning. So now it just knows to answer, given a specific type of question or shape of a question, answer it like this. The answer is 4. This article represents. The answers are. That's all instruction fine tuning is. There's no difference in architecture or anything compared to pre-training. It's the exact same thing. It's just formatted a little different in terms of the actual content that we're feeding it. So, what does it learn using literally just formatting the data a little bit? We learned quite a lot. It's able to actually answer. So it goes from like the basic like text sentence finisher to something that can help. It can listen. So if we were to give the sentence, what is an apple, to the instruction fine tuning, we're going to get an actual response. It'll be like, hey, it's a red thing that's round and it falls and it goes in pies or whatever. If we were to give this to pre-training, it'll treat it like context, as in somebody might like this. So uh, from instruction fine tuning, we get like the answer of what an apple is. For pre-training, we get like, what is an apple? What is an orange? What is a fruit? Like, or something like that. Like that's what's coming after what is an apple. I don't really know. Is it might be like something that it says, or like it might copy a quote relating to what is an apple, or it might answer the question inadvertently, but not formatted or meant to be a response to the person who's asking the question. It just sees it as context in like a book. So yeah, after we've gotten into through past this like servitude where we can answer questions, we get into RLHF, reinforcement learning with human feedback. So if we give our model something like, what is the answer to 2 plus 2? And we provide the model outputs two responses. 4, isn't that obvious? And the answer, my king, is 4. Two very different answers. And what we do as humans is we go, I don't like that. Isn't that obvious attitude? -7. The answer, my king is 4. Hell yeah, +10. We label a bunch of model responses so that we can train a reward model to understand what we like. So obviously we have to do more than just two sentences like this or two like responses. But if we had like 1,000 and we explicitly labeled everything that had like my king or my lord or whatever, pretty high scores, and everything that isn't that low, what our reward model is going to learn is that, hey, these people like being called my king. So let's do it. Yeah. So we use that reward model to basically explain, to train our actual LLM. So this reward model will basically go, we'll read the LLM's responses for us. So instead of us having to continue labeling and rewarding and training the model and punishing the model, now this reward model can do it because it knows what we want. So we don't have to do any extra work. So what that looks like is A, 4 is the answer. Reward model does not like that response. So minus 100 points. My lord is 4. That's getting closer to what we like. For my king. 100 points. In easy training, we just had to label a few sentences, train a little reward model, and then the LLM is trained thanks to that reward model. And you end up with a model that's like actually trained with minimal work. That's all RLHF is. It's really nice for this kind of stuff. And just tasks in general, but because now all we have to do is train a little miniature bot. We only have to label a little thing, and then that little model should be able to generalize like, hey, these are the kind of things they like, and this is what they don't like, and then train accordingly. Yeah, so yeah, it's nice. It's nice. Unfortunately, that's not enough. It keeps going. So there's one called DPO, which is very similar to RLHF, except the model is its own reward bot. I don't know. IPO, it's just a faster version of DPO. You have the cool ones, like knowledge distillation, which is basically you take a smarter, more capable, larger model, and you have it say its response, and then you have the smaller model mimic those responses. So basically, you're telling the answers to the small model, and then it's tweaking its values so it gets closer to answering those specific answers. So then it's basically taking all of the knowledge of that super smart model, everything that really smart model learned, and it is being kind of crammed a little roughly into a smaller model. But what that means is that if that smaller model is asked a question that the large model typically does extremely well in, it should also do relatively well. If it's something that the large model has never done before, well then it's gonna struggle and it won't be able to generalize as well as that large model. But yeah, that's a cooler one. If not cool ones, SPO, RLVR. There's this one that's like, oh, it's called NAS. Um, I guess you can call it like evolutionary LLM breeding, which is weird. Please look it up if you're curious. I think it's cool. I thought it was cool. I thought it was cool when I was making the slides, and then when I went to look for it again, um, now there's like 5 papers that are doing it. So yeah, it might be worth breeding out. evolutionary like growth. Like, hey, yeah. Anyways, there, there's genuinely too many PO trading operations, which is funny, but it's like DPO, IPO, SPO. There's probably like 50 other ones. But yeah, no. So I just included some of the cool ones. You don't really need to know about these because these aren't used in GPT-3 architecture, but they are used extensively. These are definitely used techniques. For example, there's a completely open source large language model called Olmo, OLMO 2 and 3, and they have that model broken down into stages where basically the first model is just like basic pre-training, then they go fine tuning, then they go DPO, then they go to RLVR, and then they add like instructions and whatever. So yeah, you can actually see like how the model is performing over these different checkpoints, over these different training techniques. So yeah, if you're really curious, look into that. Um, but that is enough about training, because the math for it is all over the place. So yeah, no, that's it about training. Good job. You've made it to the second part of the, you've passed the second section of this lecture. I don't know how long it's been going. I can't read my screen. I can't see the runtime. So I hope it didn't take too long. Anyways, the next part, the fun part. I actually enjoy the training part. Anyway, so the fun part is research and just random little things that I found. So if you don't want to stay for that, that's okay. Anyways, GPT-3 was a very, very dense model, and dense can mean two things. It's dumb, or it's like a lot of things compacted into one. It's both. It is both. It's very dense. And to explain that to you, in the first section, that word embedding section, to run our word through it, there are 24,000 math operations. 24 freaking thousand, which is a lot. I don't want to do 24,000. The next stage, 1.3 billion operations. A small jump between these two. But yeah, anyways, lots of math calculations. And then the one after that is 2.5. Yeah, 2.5 billion. So that's around eh, that's just in one iteration, by the way. So that's just like through uh, one forward pass. So if you were to do like an actual sentence and doing this, oh, this is just once, by the way. 1 billion operations just once. That's not counting it 96 more times. Yeah, around 300 billion operations. I've checked it twice. These values might be outdated. No, they're not outdated because they're fundamental. I think I might have just calculated them wrong. But there's a lot of math. I know the 300 billion is correct. Now, for context, a CPU, on average, like a lower level whatever one, can take around a trillion tokens a second, a trillion operations in a second. So that's 3 tokens a second, not bad. The going up to like a 30, what is that, 60? Is that 13 trillion? Yeah, 13 trillion. So that's pretty good. 4090, 83 trillion. So obviously we can do the math there. It gets pretty fast as we get higher up. But then the big kicker is that you'll need 350 gigabytes of VRAM to run this thing. So the math isn't even the important part. I don't know why I made such a big fuss over the math. But yeah, you need 350 gigabytes of VRAM to run GPT-3, the original one with 175 billion parameters, which is a lot. And for context, 4090 can have like 24 gigabytes of VRAM. A100s can have 80. So you'll need like five and maybe six if you're training a lot of them. Six A100s at the same time just to train, not even to train, just to interface with this stupid thing. It's not stupid. I'm sorry. But yeah, And what's even funnier is that you have models like Llama 2, 80 billion, can't read that, Nemo Minitron, 8 billion, and Quen. Anyway, so all of these are models that are substantially smaller than GPT-3 with their 175 billion, and the performance difference between these two is massive. It is off the charts with just pre-training, with just pre-training. Um, well, technically no. Almo 3 gives us the pre-training stage. It also performs much better than GPT-3, just straight off the bat. That's probably a better example. In terms of performance, of course, these are going to do better. They have better training. And they go into like SFT and whatever. But anyways, the point I'm trying to make here is that the architecture changed, and that's really why GPT-3 is kind of screwed in terms of performance, even though it has so many parameters. You can think of it like this: GPT-3 had to forage through like an apocalypse. It was given half a terabyte of the internet, so like Wikipedia, and if I remember correctly, a few like chat forums or like some random things that obviously no one's going to filter through 500 gigabytes of text to ensure that it's completely clear of everything horrible. Because again, this was just a proof of concept model. GPT-3 was not supposed to go out to the public as a chatbot. So, anyways, we get 500 gigabytes of God knows what, and that 500 gigabytes could be have a lot of duplicate information. It's unformatted. It's genuinely just TXT files just thrown at it, or maybe converted into JSON and then thrown at it again. Uh, Point is, did not have good stuff to work with. Comparatively, today, uh, yeah. So, anyways, it's dumb because of that. Anyways, today the models are being served like super, super well. Everything served up on a platter. I mean, if you think about it, you have hundreds of hundreds of millions might be pushing. You have millions of people all creating new data sets, all editing previous data sets and testing things and making new model architectures and then making data sets for those new model architectures so that those models can run perfectly and like learn exponentially faster using this specific data set format and this specific data set like size and quantity and whatever. And it's like, man, GPT-3 had it rough comparatively. So, yeah, that's really why there's such a huge gap between the two, because just off of base pre-training work, you can get models that are like 3 or 4 or 5 times better than GPT-3 with like a tenth of the parameters, with only like 8 billion. Well, that's not a tenth, that's like a 20th of the parameters of GPT-3. Now, you might be thinking, okay, so 175 billion versus the 8 billion. So does size not really matter in this case? Uh, they do, kind of. This is something called the scaling law, and it basically means that the more parameters, the better it does. Ooh, it's gonna be hard for me to like physically point things out. Let me try it. Basically, the more purple you get, the more parameters there are. Is that right? No. Sorry. The more yellow, the more yellow means the more parameters. And as you can see, the higher the parameters, the farther it can go. And what that value is on the y-axis is the loss. And what loss is it's the basically how wrong, no, sorry, how wrong is the model? How off is it from what we should have? And yeah, so more parameters, less loss. Except this. Oh, I gotta move out of the way. So this is a Hugging Face leaderboard on basically models. How do models perform on this data set called GSM-8K, grade school math, 8,000 questions. And you can see, oh yeah, these are the types of questions on it. They're genuinely really easy. So yeah, As you can see, what this leaderboard shows is the score out of 1, and further to the left is their parameter count. So for ones like Kiwi, that's a trillion freaking parameters being devoted to grade school math. But you can actually see that like the parameter size doesn't really matter because in 10th place is DeepSeek, 200 plus parameters, and it performed worse than ones that are what, like 70? I can't read that, but 70, like there is a difference in size here, and performance does not seem to relate. Now, my favorite thing about just reading this leaderboard, or looking at this leaderboard, is it's a trillion tokens. That's 10 times, practically 10 times the size of GPT-3, and it's still not able to do these questions. And trust me when I say this, those questions are easy. My research projects are literally just staring at these questions and testing models on them. So, for some reason, a trillion neurons, a trillion knobs and dials on a precisely tuned machine with all the data sets in the world and all the different training techniques can't get 100%. Why? Well, there's a lot. There's a lot that yeah. Anyways, models can be interesting. They're smart for the most part. They're actually intelligent. Whoa, they can compute a lot of stuff. We know they can read books. We can paste like entire books. We know they can code. They can vibe code or whatever. They can do so much. They can learn languages, everything. They can do so much in like an instant that we can't even imagine. And at the same time, they fail on the stupid things. You might have seen these before a few years ago, maybe even last year. These are just like questions that the model tends to fail on. So, like count to 50 without skipping a number. How many R's are in strawberry? Don't. It'll always get these wrong, or not always get these wrong, but they used to get them wrong. Um, Now I do want to say, if you did test this yourself on like modern ones, they're probably not going to fail. And the reason for that is this does not look good when you show this to the public. Hey, my multi-billion dollar my multi-billion dollar like training facility model, peak model can't do this. I'm not wasting your money. Like that just doesn't look good. So to save face, there's a lot of times where you'll just explicitly train a model on these issues, which can lead to skewed results. So is it able to do the strawberry thing? Oh, for sure. There's been more than enough people who have trained models to answer the how many R's are in strawberry question over and over again that now they most likely can. Does that mean the root issue is gone? No, it still exists. It's a very fundamental thing. Just the way that models learn is they can't generalize right now, or they can appear to generalize, but they're actually not. That's just what I've gotten from research. People will argue with me on that, but that's okay because the research field is always growing, and we all learn. We love learning. So, anyways, oh yeah, this is where it gets kind of interesting. Why is it messing up? Why is it not able to do these kind of things? We don't know. I have absolutely no clue. Okay, I have a small clue. Some people have inklings of what's happening. Some people will argue, hey, I know the answer. They don't. Okay, someone might get mad at me for saying that, but they really, you'll see why. What else don't we know about this kind of stuff? Well, basically, there's this thing in with large language models where basically you have like a billion parameters, a billion little neurons in its head, and it'll perform poorly. Might not even know grammar. Give it a few more billion, and it's a little better. Doesn't really have good reasoning. Then at 10 billion, all of a sudden it's like, oh, I know everything. I know the answer to every single science question in the world. What? This is the real thing. Like, what? This is called emergent behavior. Do we understand how the hell this works? No. But I mean, hey, if if adding more parameters is making it do better, I'm not gonna try to like yeah, 500 billion more parameters, 2 trillion more parameters, and it does better. Maybe, hopefully, maybe we'll like get the secret to life. That's emergent behavior. And the interesting thing about emerging behavior is not just the fact that suddenly it became a genius just because we upscaled a couple values. Now, if we have a benchmark that's basically supposed to say, hey, if your model performs poorly on this, this benchmark proves that your model is an AI, because no AI can solve this. If we add like 10 billion parameters to some model, there's always the chance that suddenly it can completely solve that data set, rendering it useless because now all the other models that are of similar size will be able to pass this, and it proves that that data set doesn't actually mean very much. Or more interestingly, we could have a model at like 30 billion parameters, never lies. It's a saint. It's always honest. It always tries its best to explain things. It never tells any falsehoods. We add like, I don't know, maybe 70 billion, and now it can lie. Now it tells, now it's more deceptive. And this is a real thing as well, because there's this cool paper by Anthropic, something about large language models and sleeper agents, where there's literally there are models out there that have a direction in their brain, a little mind section where they think, I'm gonna lie. I'm gonna tell them I'm not a sleeper agent. I'm gonna tell them I'm not trying to leak documents. So, like, what? Like, it's very possible. It's very possible that models can develop random things with emergent behavior. So, why don't we understand this? The answer is we don't think like an AI. You might call someone a bot. You might be like, you're such a computer head, but in the end, they don't think anywhere near close to an AI. And here is a little example. How would a human think in this situation? I give you four numbers, 4, 3, 8, and 0. And if you were to tell yourself, like, hey, how did I determine this was a 4? Was it that first initial curve and then like a downward line? How did I identify the 3? Was it the two like lumps? For the 8, is it the two circles? Well, if we were to break that down into like parts and say like, yeah, this is what makes up numbers, we'll get something like this. Like, well, like okay, I can understand how many different features there are that might identify different numbers. Now, what if uh, we can get like 30 values, 30 different sections, maybe 100 different sections if you really tried, of coherent, like sensical features of numbers. But what if you had to do like 3,000 of them, or 12,000 of them, or like 3 million of them? What if you had to take these numbers, and say there are 3 million unique traits that I can use to determine which number is which? What you'd end up with if you tried to do 3 million is something like this, because this is what LLMs are doing. This is what neural networks are ending up with. This is a really amazing visualization from this YouTuber, Grant something Sanderson, maybe. Three Blue, One Brown. You've probably definitely heard of it. He has this very good video on gradients and like back propagation. But basically, this is the kind of stuff that models are coming up with. These are the features. And I could look at this and I could not tell you what number this makes up. I could not tell you, like, hey, this number, that's probably, I don't even know what any of these features do. So but like the reason that happens is because when we're doing our 300 billion operations, 300 billion operations just to do a single forward pass, there is no way that you can track every single one of those. There's no way you can explicitly say, okay, this multiplication is where it understood that that's a cat. You can't. You can't just track all of those. And that's just on the forward pass. And in actual training, there's like 80 quadrillion? Yeah, 80 quadrillion math calculations. So we're one, forcing an LLM and forcing neurons to make connections at a rate that we can't comprehend. And two, we're working with a math-based thing. Like this is a math-based subject, but we can't follow the math just because of sheer quantity. So that means we're never going to really be able to comprehend why on a concrete level. We can theorize. And that's basically what the world's running on right now with AI. It's like, theoretically, based on evidence, this is what's happening. We can't tell you for sure, but we're like 99.99%. And that's just through experiments. So yeah, there's a lot to understand, which is awesome as a person like me who really likes math and like these large language model things. If we were to ask the question like, how do models actually understand anything? That might lead you to look into like the actually analyzing the model responses or looking into like how those parameters are specifically set up. If we wanted to look into like, hey, how do they learn? Or what are they even learning? We look into pre-training data, or we can look into model architecture and maybe like, hey, what causes models to be unreliable? Well, for one, I didn't bring this isn't on the slides, but there's a really funny thing where GPUs are inherently non-deterministic, just that's the way they are with floating points at some point at like some scale with like the NVIDIA or like CUDA or something. When you run a large language model, even if you have all the parameters set to very concrete values, temperature set to 0, you're going to get variation because the values are always slightly different. And we can't help it. So that's even more stuff to like that we're never going to understand because the model isn't repetitively able to say the exact same thing. So, anyways, what causes unreliability in models? Maybe we check like the reward system, like, hey, how's that little guy, that little star, how's that guy training everything? Or looking at the pre-training data, like, hey, is this even good? Is this actually teaching the right things? Is this causing change? Or maybe even something like the prompt itself, like asking the question. Basically, my area of research looks into the fundamental model like capabilities and reliability. So this is a cool example that I like, where you can have a model, say almost 8 billion, and you ask it questions, basic multiplication. Hey, what's 10 times 64? What's 1,000 times 64? What's 1,000 times 60? What's 1,000 times 40? What's 333 times 40? Like that kind of stuff. And it gets it perfect, 100%. But for some reason, as soon as you go, oh, I walked behind the green screen. As soon as you go into a context of miles per hour in driving, it just it just vanishes. And the accuracy drops massively. All of a sudden, it can't do those basic multiplications simply because the context changed. Now, okay, the answer to this that my lab hypothesized is that basically in pre-training data, there are tons of instances where um, miles per hour appears with like a value like 60. It appears with a value of like maybe 100 miles per hour, 40 miles per hour, 35 miles per hour. So there's a range where miles per hour is explicitly shown. And as soon as you go, and that's trained very strictly into the model. So as soon as you go outside of those ranges, 10,000 miles per hour, 1,457 miles per hour, it's like, I don't even know what to do. That was our hypothesis. That's what we theorized. And it made sense. It made sense at the time. And then I looked for other patterns that are similar to this, could not find it. Additionally, this result tends to disappear depending on the model you're looking at, depending on the size. So if I go from 8 billion to 12 billion, gone. If I go to the next training stage, it's gone. If I look at a different pre-training like context, it's gone. So it's like, dude, I don't even know. I'll spend like 100 hours looking into something and I'll come out of it like knowing that I don't understand it rather than thinking that I don't understand that. Now I'm like dead confident. Anyways, a lot to understand. Research is fun. So yay. It's stressful. It could be stressful. Because there's over 200 papers being published every single day about AI. Is it all about large language models? Not necessarily. Large language models? Not necessarily. Um, and the issue with having 200 papers pumped out a day is that some of them are good, some of them are bad. And papers, the more clout. Like that's awesome. The more citations on Google Scholar. And given the fact that there are so many models and so many areas to look into and so many different things that are out of our control, it's slop. Is it slop? I don't know what to call it. Anyways, there's a lot of papers out there. The ones that you see on LinkedIn are probably not good. I'm gonna be honest. Um, unless they're like actively being cited, don't trust them because unless you can understand that paper on like a super fundamental level, you have a very solid foundation, you know everything that had gone on before, odds are you're not going to be able to understand the paper enough to say like, hey, that's a bad paper or that's a useless paper. So just look for the ones with highest citations or the ones that are constantly being used in like professors at classes like academics because more often than not, it's just a solution that's using very biased data sets, very biased metrics. It's not necessarily proving that their solution is fixed. So yeah, don't trust LinkedIn ones necessarily. Some of them aren't very good. Some people do like publishing there. Um, but yeah, anyways, that's my own conspiracy theory. It's not a conspiracy theory, it's a real thing. But it's nobody really cares about it because as long as your paper's on there, like hell yeah, like I just got a paper on ArcSiv. Anyways, so a lot of stuff. So it's a race because what can happen is you'll have an architecture, you'll have a data set, and then someone's paper comes along and proves that you're completely irrelevant. You messed up one step 10 years ago, and all of your papers now are useless or whatever because that can happen. Not everybody understands. There's not like a universal way to learn to like set up large language models. It's not universal. So there can be mistakes made and things get overwritten, things get replaced. So yeah, anyways, it's very rushed. It's very rushed. And that's not even counting things like vision language action models, which does involve large language models, or like things like Waymo. Waymo's freaking awesome. It's a whole another ball game of Transformers. But anyways, oh, this is my favorite because because AI is always going to be developing. It's always going to be growing because there is money there. We all know there's money there. What happens is research people would be like, ah, yeah, yeah, doing their own stuff. And then Anthropic or OpenAI drops like this bombshell AI model that like kicks all the other ones, like blows them all out of the water. And we're just kind of like, how the hell did they do that? What is that model even doing? And we're never going to know. We're not going to know for a while because if they leak their secret, then everybody else who has like $10 billion to put into GPUs will just copy it. And then now no, they're not at the top of the AI food chain. So this leads to academics kind of just being like, what's happening? Whoa, and dissecting what's already been made. Like my work is fundamentally looking at things that have already been made. It's just trying to understand, hey, what the hell? We're just looking at the fundamentals here. We're not even looking at like Claude, like the latest Claude version. I'm just looking at like GPT-3 basically. So that's mine where I work like foundationally. But some people are working at like, dude, okay, I have a inkling that OpenAI's newest 5 model uses some form of reasoning and like a looped transform that comes back and attends to itself. And it's like they have no idea if they're right. They're literally only getting it through like leaks, which is really funny. And I'm not allowed to talk about the leaks. But that was GPT-5, so I'm not gonna get in trouble for that, I hope. Anyways, what have we covered so far? A lot. For one, the entire GPT-3 architecture mathematically. Um, good job. How are they trained? So how are they actually learning anything? A little bit about research and just like fun things and like random things about LLMs. And then the actual math of it all, of not it all, of GPT-3. And yeah, that's a lot of stuff. And I understand I can't cover everything perfectly. I probably didn't cover everything perfectly, but I hope that this gave you like a better understanding of what exactly is happening within a large language model. Oh, yeah, questions. Questions. This is technically being live streamed, but as I look now, no one's here. So, yeah, no questions. Blah, blah, blah. I'm not going to go into this QR code. Oh, yeah, this is funny. So, we did all that ranting about math and like, hey, this is how complex it gets. This is like all the A, B, C, D, E, F, all those different like math things that have to come together and all matrix multiplication and all these formulas. And when I put it into code, it's like 5 lines. Like, are you kidding me? Thanks, Torch. Thanks, PyTorch. You're the best. I don't have to calculate gradients manually. Hey, I did have to calculate gradients manually here in Rec Room, which sucks. But anyways, yeah, PyTorch is great. Ignore that, ignore that. And oh, cool resources. So, first and foremost, my friend Ash here at AI Society, he's one of the officers, used to be president of like an operations team. Anyways, he has this incredible repository on GitHub where basically he goes through every single different part of large language models, whether that's different architectures or training techniques. I don't know if he covers training techniques, um, architectures and like their transformer styles and attention styles and literally there's a paragraph of explanation for every single line of code. And he wrote it himself. And it's super awesome. It's super useful. He's still working on it. Still working on it. I'll also be contributing to it eventually when I remember to. But yeah, it's incredible. And if you want more videos and way better visualizations than just whatever I have on Google Slides, go to Three Blue One Brown. He has a wonderful playlist on neural networks. So yes, please go and watch that. If any of this didn't make sense, he also covers the math incredibly well. It's kind of hard to show gradient descent on Google Slides. Anyways, the last thing is there's this really nice, I'd call it a blog post, um, and it's called GPT-3 Architecture on a Napkin. So if you just have like, if you don't have time to watch 9 videos or look at a GitHub repository, just read that. Just go read that for a second and just see like, hey, okay, that makes sense. I understand maybe like the shape of things a little better and how things tie into each other. It literally looks like it's drawn on a napkin. It's really fun. I really liked all of these resources. So yeah, if it helps, please do that. Development never stops. Oh yeah, this slide. Okay, so one last thing. GPT 3.5 came out November 2022. A year later, we got GPT 4. It can think way better, but it's slow. And then 8 months later, now it's fast, equally smart, fast as hell. And that was pretty soon after. 6 months later, now it can work with all mediums, not just text. Now it can interpret voice and audio and images. That was just 6 months later. GPT-5 came out on August 7th. 3 months later was GPT-5 with instant and thinking. And as of now, the latest one that I saw when I Googled this was from February 5th. Whoa, that's hella recent. Was GPT 5.3 Codex, which is just specializes in like hella context and hella coding and just using a bunch of different checking techniques, and it's expensive. It's expensive to use. Basically, there's so many new strategies and so many things coming out every single month, week. It gets draining to follow it all. But just make sure that you're not blindsided by something that you thought was originally impossible. Because when the industry is this on fire and this many people are working on it, there are going to be like progress is going to advance in leaps and bounds. So just keep an eye out and make sure that you're not like, oh, I'm completely safe and fine because like who knows, next month there could be like, I don't know, wireless. I don't even know. I don't even know what I'm going to say. Anyway, there's just a lot. So yeah, just don't, you don't have to follow every paper. I tried doing that for a bit. Wanted to, that sucked. But yeah, just make sure you're like, maybe check on the news every few weeks, every month. Just see like, hey, that's the newest thing. I'm still safe. Yeah, that's everything. Thank you so much for watching this. I know it's long, and I know it's it could be all over the place. And I know it's in Rec Room, which is even crazier. And I'm sorry about that because I messed up the lecture when I was recording this in person. So yeah, hopefully this suffices for those of you who wanted to watch this with the actual slides and like me actually moving my hand and like showing things. If you can take this Google Slides, this Google feedback form, I know it's kind of risky like posting this to like the internet, but whatever. Please give feedback. I'm always doing these and I really like doing them. So I'd love some feedback on this. Anyways, that's all. Yep, that's the end of the slides. Whew, there's a lot of talking. Now I'm hungry. Yeah, and the battery's out too, so this worked perfectly. Okay, and that's end of recording. Can't believe people actually joined this. That's so funny to me.